Hi, everybody, and welcome to my presentation titled Implicit versus Explicit Data in an Item-Based Collaborative Filtering Model, which I'm sure you all understand right off the rip, but we're going to go in a little more depth. I'd like to say thank you to my advisor, Mark Cravella, who guided me through this whole process from pretty much never having heard of a music recommendation system to building my own from scratch. So, what was motivating me to take on this project? First of all, it's my own personal use of Spotify. Anybody here use Spotify? You guys use like the Discover Weekly or the radios or the mixtapes? Okay, so I wanted to know how those worked a little bit better. And I also wanted to see if there were ways to improve those recommendation techniques. And I wanted to do that by researching a particular type of recommendation model in depth and then trying to understand some of the nuances around how those models are formed. So, a little bit of a big research question, but we're going to break it down in the following slides. In a standardized item-based collaborative filtering model, it's a mouthful, do implicit user music data or explicit user music data produce more successful recommendations? So basically what this question is asking is, when you touch your phone, you use your computer, and you create actions while you're using Spotify, we call those explicit, versus when you kind of unknowingly create data, we call that implicit, and I want to know which one of those provides better recommendations in this kind of closed experimental system. Here are some of the challenges. First of all, limited data sources. For example, Spotify users don't give like a 5-star rating. They don't give any ratings, actually, which makes it really hard to do. Sparsity, which is there's something like 600 million songs on Spotify, and if I told you I listened to 1 million of them, you'd be blown away. So there's a very, very small subset that each user has of actual listened to items. And also comparing across data sets is very difficult because they come with different sort of statistical issues that we'll go into a little bit later that you have to correct for to be able to cross-compare. Okay, so this is what my data kind of looks like. It's a little bit of a play data. In the top, you see playlist matrix. So the columns have these actual playlist names, so workout and party were the ones that I chose. And then on the rows, we have the names of the items or the songs in that particular playlist. And since this data is really difficult to use, I had to basically assign it a 0, meaning it's not in the playlist, or a 1, meaning it is in the playlist. And that's as deep as that data goes. Below, we have the play count matrix, which has people as the columns, so users like anybody in the crowd. And then similarly on the rows, we have the same selection of songs. So the playlist matrix is going to act as our explicit data because my assumption is that users actively put things into a playlist. They want it to be there. And the play count matrix is implicit data because users unconsciously, they don't know how many times they've listened to a song. It's not recorded for you anywhere. You just listen to it as much as you want to, and then that number gets stored elsewhere, which I can use to generate recommendations. Okay, so now we're going to talk about collaborative filtering. I have this cute little diagram that I put together. The basic idea behind collaborative filtering is if I am the active user, the person who's being recommended for, in a normal life outside of computer science, I might go and ask friends, hey, what are you listening to these days? Or I might go online and find communities of people, rocklovers.com or whatever, and get a recommendation from there. So the idea is to take your active user through some various means, find other really similar users who have listened to a particular item that the user you're recommending for hasn't, and say, if these users, other friends of this user, let's say, who listened to this item really liked it, then it's likely that the user will like it too, since they're so similar. That's called user-based collaborative filtering. In my model, we do it a little bit differently. You can think of the items are asking each other, so they're kind of like the people, hey, we're similar to each other, so since the user doesn't really know anything about me, but he knows a lot about you, then maybe we can kind of feed it into the user. So you can kind of imagine switching out users for items, and that's what makes an item-based collaborative filtering model. Okay, don't get scared. We're going to go through the math. There's 3 types of similarity coefficients, and what these are used for is ranking the neighbors of the active user. And basically, depending on how you calculate these similarity coefficients, your model will produce different recommendations. So for example, this first similarity coefficient is called Jacquard's. It's basically how many items are similar over the total amount of items. And that produces a really basic idea, like percent similarity you can think of it as, versus these bottom 2, Pearson's correlation and cosine similarity, which produce a much more complex pattern in the data, giving us a different set of similar users, which isn't necessarily better, but can potentially capture more of the data. Okay, this is the whole model kind of spelled out, quote unquote. In order to build these models properly, there's a lot of smaller models, basically, that you have to build up and combine into one large model. The first thing that you have to do is correct for biases. So for example, if I rate things on a scale of 3 to 7, meaning 7 is something I love, and I never use a 10, it's too high, whatever, and 3 is something I hate and I don't bother going down to 1, and then some other arbitrary user uses 1 to 10, their 10 and my 7 is the same rating effectively. But when we go to recommend things for them or understand their rating patterns, that's not easily corrected for. So the first thing we do basically is understand how a user rates. What's their inherent scale? Or understand how an item is rated. Does it tend to be rated in a certain way, which we need to correct for to ensure that recommendations are objective and standardized across the whole model. Second is something I already mentioned, similarity coefficients. This is the method in which you find similar neighbors to then go and quote unquote ask, hey, what were you rated? Were you rated well? Does that seem like something we should feed to the active user? The most important part of the function, the predictive function, takes all this different information about biases, about similarity coefficients, and about specific information from the user and from the data sets, the playlist data and the play count data, and basically puts it all together into one equation, does a little bit of math, and spits out a rating that is of the similar scale of the data set which it comes from. So for example, if I was asking it to predict on the playlist data, which is 1s and 0s, it would spit out a 1 if it thinks the user would like this item, or a 0 if it thinks the user wouldn't. And on the play count data, meaning how many times the user has listened to something, if this user on average listens to something 20 times, the user really loves, and 3 times it kind of loves, and 0 if it doesn't, it plays on that scale as well. So basically, the predictive function uses the inherent scales of the users and the items, as well as the similarity coefficients and the biases, to produce a rating that is accurate enough to potentially give to the user. Finally, we have the one-out function, which is really cool, I think. To ensure that the model actually recommends things successfully, basically what you do is you take one piece of data out of the model, one singular number, you ask it, what do you think that data should be, and you compare what it generates or predicts to the actual value to see your error rate. Okay, this is a quick aside. The data sets have 2 different sort of ranges of data, so you have to normalize them so that they're comparable, and that's called the normalized root mean squared error. It's a big term, don't worry about it. Basically it means that whatever the recommendation, the error rate was before, we're gonna put it between 0 and 1 and use that as a success metric to be able to compare across the data sets. And that will make more sense when you see this, which is the results overview. I'm gonna use the pointer for this one. So these more flat lines here come from the play count data, and this green line here comes from the playlist data. And the idea is the lower the error rate, as anything else in life, the better. So you want to be misrecommending or mispredicting as little as possible, reducing that overall error. And what this data suggests actually is that the play count data, which is the implicit data, seems to have a very low effect of asking neighbors for recommendations. So it starts off actually decently accurate, and then it stays sort of moderately accurate the whole time. And there's no real benefit to adding more than, it looks like, 1 or 2 neighbors potentially. Conversely, the playlist data has the exact opposite relationship, where it starts decently inaccurate, relatively inaccurate, and then as you add more neighbors up to a certain point, it becomes more and more and more successful in its predictions. Okay, so what's the conclusion? Basically, it's hard to say exactly what the conclusion is, but overall, the playlist data performed better, suggesting that basic patterns probably do capture user preferences. And so you don't need to sort of, quote unquote, go all out in your recommendations. Just try to capture really basic patterns and use those to generate decently accurate recommendations. And the sort of big, quote unquote, takeaway is that K-nearest neighbors is actually really bad at this. So I chose a pretty bad model for this whole project. Only now I can see that after finishing it, of course, because that's how these things tend to work. And other sort of bigger problems in the model, such as data sparsity, turned out to be enough of a negative component to really push the results away from being super interesting and significant. But overall, it was a great project. I learned so much from just building this model from scratch, and I think that's where the real takeaway was for me. So thank you, guys.
All right, we have time for a couple questions. Any questions? It's all back here, and then I'll come up here.
You talked a lot about, normalizing the ratings. How does that happen? How do you do that?
Okay, so this is sort of a long-winded answer, but I'll try to keep it quick. Basically, the predictive function comes up with a rating, and you tell it to do that like 100 times, for example. You take those ratings and you put them into a long list. You take the average of that long list, which gives you the average of the predictive function. You take the root of that average, which is the RMSE, the root mean squared estimation. And then you normalize that by dividing it by the standard deviation, which produces like a per data set normalized standard error.
All right, one more question.
What made you want to do this project? How'd you get, like, why this?
It's a great question. I mean, I love music, and I think for me, one of the most impactful and sort of lovely moments in my life is like discovering that new song that you really, really connect with. And I wanted to try to replicate that process and potentially improve it for myself. So kind of selfishly, like I just wanted more of those great moments with music.
All right, we actually have time for one more question.
Great job, Henry.
Thank you.
My question, the similarity functions you were using, like the cards, that was for the items, meaning the songs, not the user?
Yeah.
Okay, so you were ranking the songs and asking the similarity between the songs, not the user.
Yes. So
Sorry.
the quick summary for that is you basically say, instead of asking your friends what they like, you sort of look between songs and see which of these songs were rated similarly across the whole set of users. And then you find some amount of those songs called k-nearest neighbors, and you average their scores for that unobserved value to predict a new value.
All right, that's all the time we have.
Thank you.
So we'll use it in transition time, and last we'll have Katrina.